Hello, everybody. Greetings from midnight in Dublin. I won't share my video because I just don't want to overload the Wi-Fi. So thanks very much for inviting me to give this talk. I've been in Trinity College Dublin since 1997 and took a career break to go to Disney, as Matt said, and also spent a year with Jay Lee in Seoul National University. And I'm really a computer graphics person, computer animation person, but I've become more interested recently in mixed reality, VR and AR, because those are where the really big, challenging problems currently are for those of us who do computer animation, computer simulation. So let me start off just by talking about a few concepts that I've been interested in recently. So the sense of agency in human perception is the feeling that you get when you're controlling your own body and you're also affecting the external environment. So for example, if you were to pick up a ball and throw it, it's the feeling that your own body has created that action, and that the response in the environment to your action is appropriate, and that gives you a feeling that you're actually affecting the world. Now, there's some research that shows that when the computer assists too much, perhaps with an intermediary device or giving too much help in actually creating the solution, that you actually lose that sense of agency sometimes. And that's even if the computer completes the task as you wish it, that you lose a sense of agency. So this would seem to suggest that agency would be greater when you're using your own body to launch a physically based event. So for example, here on the left-hand side, you see a kind of a thought experiment of a person in the real world throwing maybe a real ball into a virtual part of the world. It could either be full VR or somewhere along the continuum to simply the ball being virtual and the two people being real, or a virtual entity in your real world. So what's also important to agency is something that I've been studying in relation to computer animation for quite a few years. So the perception of causality it occurs when an event is perceived to cause a particular physical response. So for example, a ball hitting another ball, making it move. A ball hitting a table causes it to bounce. And over here on the right, you actually see Albert Michotte, who in KU, Catholic University in Leuven, who back in the 30s and the 40s built this extravagant apparatus to create very simple images of rectangles bouncing off each other. And in this, he found various different effects that can control whether you perceive something to be causal or not. Another interesting thing about this perception of causality is established extremely early in life. So your ability to determine whether an event is causal or not actually occurs in infancy. So if you see here, there's been quite a number of researchers studying young infants. So here, for example, the child is sitting on its parent's lap, looking at causal and non-causal events happening on a screen. And they're able to tell by the attention that the child pays to these various different events, whether or not they think it's surprising or not. And they found that infants as young as 3 months old are actually able to distinguish between causal and non-causal events. And it's actually easily broken. So if, for example, there's say here, for example, two billiard balls, let's say they come into contact, and then there's a delay, which can very often happen in real-time events if there's a lot of calculations going on, calculating collision response and contacts. A delay can occur, and this breaks the perception of causality. It no longer looks like one event caused another. It actually looks like there's some kind of animacy in the objects they're moving under their own steam. You could also have overlaps if the two balls, for example, overlapped when they came in contact, or if they didn't come in contact and bounced off each other and leaving a perceived gap, that they also break the perception of causality. And also here, for example, if you imagine this is a cue ball in billiards, bouncing off the ball here, and the ball goes off on its post-collision trajectory, and so does the cue ball. If you distort these angles and they don't come off the way that they're expected to be, that could also break the realism of the interaction and the perception of causality also. And now there's also been research to show that the perception of causality is intrinsic to a sense of agency. So those two concepts together will allow us to think about how do we do these kind of interactions, physical interactions, and make them compelling in virtual reality and augmented reality. So we might, in virtual reality, you would have a virtual body and a virtual object. What would happen if you were trying to get a virtual character who you're sharing your real space with and throw them a real object? Is that something that's something quite futuristic? What would we need for that? Catching. So these are the kind of things that we want to do within this new world of interacting in a natural way in your own environment. What do we need? Well, there are many things. We need to study causal perception. We need to do physical simulation and character animation. We'll definitely need AI, both in terms of machine learning in order to learn how to do these interactions properly, and also in order to create maybe an intelligent partner, an intelligent 3D character within your real world who will play ball with you and throw ball at you. We need to look at capture, we need to look at haptics, maybe we need some kind of robotics that will allow a ball to be thrown back at us from a virtual character. So those are the things that we need. So I'd like to maybe just talk now about some previous work that I've done that kind of leads into this new area of mixed reality and physical interactions. So I started off looking at collision detection, collision response, physical simulation, and also looked at the perceptual aspects of this. So I ran experiments where I was looking at the kind of distortions that are tolerated in physical simulation. I'll also talk briefly about an experiment that we did where we captured the motions of somebody throwing a ball and then looked at various different distortions of the trajectory of the ball and which of those are acceptable to viewers and which were not. And then also character-character interactions. So what are the similarities and what are the differences when you look at collisions between simple objects like balls and rectangles and cubes and real humans who are pushing each other or interacting in some way. So for collision detection and collision perception, very often it can be an expensive process, especially if you've got complex models or whatever. So you often make simplifications to the physics. So there on the right, for example, you have collision proxies that are being simulated with bounding spheres, whereas you're actually looking simply at the polygonal model on the left. And these kind of things can cause distortions. They can cause those gaps. If you didn't use the bounding hierarchies, if you would end up with intersections and overlaps. If it's too slow, you'll end up with timing delays. So all of these things can affect your perception of causality. And those are something that I explored in my early work. I was published back in 2003, SIGGRAPH, and follow-on works from that. Another piece of work that I did with, and this was with the psychology department in Padova. We did a set of papers and experiments where we captured the motion of somebody throwing a ball at different distances. And then we looked to see what kind of errors can be tolerated when you edit the projections or when you edit the trajectories. So we find that people were quite sensitive. So for example, you take a motion capture of somebody throwing at a near distance, and then you extend the distance by which it's thrown further. What we found was that you can do some motion editing, some simple motion editing, where you change the angles of the arm, and that will make the throw more plausible if it doesn't match the trajectory. You can change the velocity, the ballistic motion at the point of throwing. And here what you're looking at the moment is the kind of thresholds that are tolerable, so that you can have increases and decreases in the trajectory of the ball that will go unnoticed according to our predictions. And then finally, here is some work that we did on collisions between people. So in our motion capture lab, we captured two actors pushing each other at different levels of strength, from in front and behind, and also pushing them in different directions. And then we did a set of experiments where we distorted the response of the person being pushed, where we added a time delay, or we made them move too soon, or we put, for example, a weak push together with a very strong response. So you had a mismatch in the forces between them both. And we also changed the directions. And the interesting thing that we found here was that the perception of distortions in these character interactions was very similar to the perception of collisions between simple objects such as spheres and cubic objects. So this is interesting. The only time that this didn't happen was when there was a very light push, say, where somebody pushed each other from the front very lightly. And then this would sometimes look acceptable because the humans are perceived to be animate objects, so that they would step back, it would look like that. But once the pushes were stronger, they behave very much like physically based objects. Okay, so now I'd like to talk about some preliminary work that I've started to do in VR. So we set up a system in VR where we used our full body motion capture system, but we also did a real-time throwing experiment in VR where the person is throwing. We used a Manus VR glove, used some Vive trackers for real-time tracking, and the Vive headset. And then the person went into the virtual environment, and you could see on the left there, this was the scene that they used. They would pick up the ball and then throw it at targets that would randomly appear at different positions and distances around the room. Now, we did actually try doing this, first of all, in AR using the HoloLens one, but we found that it was very difficult to do this particular task because of the field of view. And we also did the full body motion capture to use later in order to determine, learn from the simpler trackers what kind of response that we needed for throwing. Okay, so here you see on the right an example of, we captured 18 actors, 18 different actors, males and females, half male, half female. You could see that they were given the freedom to use their own strategy. So they could sometimes do underarm throws, and sometimes they would do overarm throws. And then we used the full body motion capture. So each of them did 64 different throws. So we had a reasonably good database of throwing motions. So we used the motion capture database to try and find the point of release. Okay, so we could tell from, we tried different configurations of joints and dynamic features. So, and then we used the motion capture data and tried to learn from these different configurations what the actual point of release was as determined from the real-time system. So I won't explain this in detail, but you can see here, for example, this is a 90% accuracy of predicting the ground truth using a model where we trained the model using position, velocity, rotation, and rotational velocity of the wrist joint, the elbow joint, and the shoulder joint. So not surprisingly, we get over 90% accuracy when we use all of the features. But I think what's interesting here is, for example, here, this is rotation only, where we only use the rotation of the wrist, elbow, and shoulder. And we were able to get almost equivalent accuracy as in using all of the other joints. So this could suggest that, for example, simple inertial sensors on the wrist, elbow, and shoulder would be sufficient to predict what the point of release is of the ball. And it's very important to get the point of release right, because if you don't get the point of release right, then the velocity will be wrong, the angle of release will be wrong, and you'll end up with a very implausible throw. So some future work that I would do. So this is work that I worked with Jihi Lee and his team in Seoul National University, and then followed on in Disney Research when I was there in 2014. And when we were in Seoul, we captured the motions of stunt actors who did many hours of physical interactions in fighting. Okay, so this was a fighting scenario. We captured their motions and created that database. Now, as we heard previously, contact is very difficult to predict in real time. So this could be a particularly challenging problem to solve. So for example, here, you can see that we use then this database to try and pick the most suitable interactions for a particular task. And we would rank these based on a number of factors, such as how much editing was needed to create these interactions, etc. Now, this could be very useful in a virtual reality or augmented reality environment where you want to interact with a virtual entity, or maybe an avatar of a friend who is somewhere else remotely. Maybe you want to do some fighting, fake boxing, or maybe something more benign like dancing or something where contacts are needed. So this would be something that I think is going to be a very interesting challenge for future work. So I think I'm going to finish up there and thank a number of people who helped me along the way, not just these people, but many other interns and students over the years. So thank you very much.